Okay, now we're going to get into something that is very strange and counterintuitive. It goes against our natural intuition. So already this makes sense. You know this, you probably learned this in middle school, that if we have two like charges, they repel, right? And that's obvious. So another example of that would be two negatives. We know that they're like charges, so they repel. And lastly, we know that if we have opposite charges, that opposite charges attract. Here's where we get into the strange effect. If we have a rod that is overwhelmingly positive, so we're going to draw this with just positives. It doesn't mean that there's no negatives in it. It just means it's so positive that we can just represent it with pluses. And over here we have a neutral pith ball. A pith ball is just a ball that hangs from a string, and it enables us to see what happens when we get attraction and repulsion. So if we count up, we have 5 electrons and 5 protons. I am short 1 proton. I'll put that in there. And when this positive rod comes near the neutral pith ball, the protons are stuck in place in the atom, but the electrons are free to move. So the electrons are going to come over to the edge like this. And what that's going to do is it's going to make the edge of this pith ball negative. Well, what happens if this is negative and this is closer than the positives are to the positive? Well, that's going to produce attraction. Now, the net charge of this is neutral. This is positive. So what's this weird effect? A charged rod will attract a neutral object. So you can only get repelling by like charges, but you can get attraction between opposites, and you can get attraction between neutral objects. This separation of charge is called charge by induction. I-N-D-U-C-T-I-O-N. Induction. Now, the same thing can happen with negatives. Now, this is a little bit counterintuitive as well, but remember that it's only the electrons that can do the moving. So, the protons are stuck in the atom, the electrons are free to move. What are they going to do? Well, they're going to move away from this negatively charged rod. Again, the rod is negative. We represent it only as negatives because it's overwhelmingly negative. And now these negatives are very close to the positives, so we get attraction. So in both cases of induction, we get attraction of neutral objects because of the separation of charge. Let's review this because this comes up in a lot of questions. So let's go over. So only like charges can repel. So if we have repulsion, it's either going to be plus plus or minus minus. But you can get attraction two different ways. You can get attraction between opposites, and you can get attraction between neutral when you're dealing with charge by induction. Charge by induction occurs when the electrons move over towards the positives. They're closer, so we get attraction. The net charge, 3 pluses, 3 minuses, is neutral. So neutral is attracted to positive. And then lastly, we can also say that the opposite is true, which is we have, again, charge by induction. The negatives repel the negatives. Then these positives are close to the negatives. So we have a neutral object, 3 and 3, neutral, attracting to a negative rod. This is a popular physics demo, and what we have here is a faucet with water running down. Now, what's the charge of water that's just running out of a faucet? Well, it's not charged up, so it's neutral. Remember that neutral objects attract to charged objects. So if we take a positive rod and bring it near a neutral stream of water, the stream of water will bend. What if we take a neutral stream of water and bring it near a negatively charged rod? Again, we'll have charge by induction. This will stay neutral, and it will attract to the negatively charged rod. What happens if we have someone comb their hair? Well, hair easily loses its electrons, and the plastic comb gains them. So if the comb gains electrons, then the comb becomes negative, and if the hair loses electrons, then the hair becomes positive. And the last little demonstration that can be done is where we have a balloon rubbed on someone's hair. Balloons are made of rubber, so they will become negative. The hair will become positive and staticky and start to stand up. But what if we take that balloon and bring this negatively charged balloon near a neutral wall? Well, the electrons in the wall will move away. That's charge by induction. And if we have now positives close to negatives, we get a force of attraction to the neutral wall, and the balloon will stick to the wall. So what is an insulator? An insulator is a material in which the electrons are tightly bound to the atom. In other words, the electrons are not easy to remove. Remember that the electrons are orbiting around the outside, so we can remove them, but in insulators, it's much harder to remove them. So what materials are like that? Plastic, rubber, dry wood. Now, why do I say dry? Now, the reason that I'm saying dry is, I'm going to write this down here as a little side note, is that moisture or humidity helps to conduct electrons away. So when it's wet, electrons can leave the wood. So it's more likely to be dry wood that acts as an insulator. Okay, the same thing is true for air. Dry air, if it's humid out, there's moisture in the air and it doesn't work as well as an insulator. A vacuum, which would just be empty space, sometimes double paned windows have the air sucked out to act as better insulators. And another good example is glass. Now, there's many more, but those are some of the main ones that you should have an idea of what they are. Okay, so then what is a conductor? Well, a conductor is the opposite. It's a material in which the electrons are loosely bound. In other words, they're very easy to remove from the atom. There are also things called free electrons. Now, what's a free electron? And a free electron is an electron that's just hanging out inside the conductor. It's not bound to any atom at all. It's just sort of free floating around. So what are the examples of these? These are most metals. Now, on the Regents reference table, there's a chart of different materials, and the resistivity of the material is this Greek letter rho. And that is what resistivity is. And we're going to learn the formula for that in the next unit when we start talking about resistance. So for now, resistivity is this Greek letter rho. The unit is the ohm meter. And the lower the resistivity, the better the material acts as a conductor. This is also affected by temperature. So on the Regents reference table, as temperature goes up, resistivity also goes up. In other words, it makes it harder to conduct. So you kind of know that idea because if your cell phone starts to overheat. It starts to not work as well because the battery and the electric circuitry start to produce too much resistance. So if we look at these different materials, the one that has the lowest 1.59, they're all times 10 to the 8th. This has the lowest resistivity, therefore this is the best conductor. This would be followed by copper, then gold, then aluminum, then tungsten, and the highest one that acts a little bit more closer to an insulator. It's still a conductor, but compared to the others it acts more like an insulator. That would be the material nichrome. Let's look at a couple of practical applications of insulators and conductors. Let's say that you're wearing rubber-soled shoes and you're walking across a carpet. Carpets act a little bit more like a conductor, and rubber shoes act more like an insulator. So when you rub your shoes, you get friction, and you start to pick up electrons. So you become negative. Now, as being a negative person, you build up all of this charge and save this charge on your body because your shoes are insulated and because you're surrounded by air. Now, this is going to work much better during dry air, which usually occurs during the winter. So if you build up this charge and then get near a conductor, like a doorknob, the electrons will jump from your body into the doorknob and you will get a static shock and you'll see a little flash. And this has probably happened to you before. This can also happen if you touch another person. So a person is neutral and the electrons can jump from you into the person. And it's important to know that both people get shocked. When you have electrons leave your body, you get shocked. And when you have electrons go into your body, you get shocked. The same thing, you might have noticed this happen before, is with a car. A car has rubber tires. The rubber tires are insulators. They pick up electrons and place them on the car. So now the car is negatively charged, and if you get out of the car, you are neutral. The electrons want to get to this neutral place, so they jump through the air and give you a shock. This happens a lot less frequently when it's humid because the electrons leak off the person into the air, making the object closer to neutral. We already mentioned charge by induction. Charge by induction is separation of charge. Charge by conduction is when we have contact or jumping of electrons. So when we have conduction, we actually have electrons leaving one body and entering another body. And there's a really good demonstration where you can see this in action. Let's say we start out with a pith ball hanging from a string. It starts out neutral, same amount of protons and electrons. But if we bring a negatively charged rod near it, the electrons will move far away, making this separation of charge, and so this is charged by induction. But what happens if it gets so close that we get a shock? Or what if we get so close that they touch? In that case, this is overwhelmingly negative. Electrons will jump into this sphere. Now, this is still going to be negative because it has tons and tons and tons of electrons. So that will then look like this, where we have a negatively charged rod, and now this is overwhelmingly negative, so we just draw the negatives here, and we get repelling. So the separation is induction, the jumping is conduction, and finally at the end of this, we get repelling. Let's look at this same situation in reverse. Induction, the separation, conduction with contact or jumping. So we start out with a neutral pith ball hanging there with equal protons and electrons. This time we bring a positively charged rod. Now that means that the electrons are going to move over to the edge. If it's close enough to get contact or jumping, the electrons will jump into the rod. Now, the rod is so positive that these electrons don't really matter, and this ends up staying positive. Well, what happens if we have a positive pith ball and a positively charged rod? Well, in that case, we get repelling. Electroscopes are devices used to determine charge. Now, there's two different styles of these. They are insulated. This is a metal ring, and then this would be made out of plastic. And then this is a metal knob with metal running through, but there's plastic usually around here to keep this insulated. And there's a metal rod that runs down, and then a metal leaf that is free to pivot. So if charge builds up and you get repelling, the leaves separate like this. They sort of go apart from each other.
Rod up close, and we'll watch what happens. We see that we drive electrons from the top plate down to both the movable arm and the stationary arm, and then they separate from one another, indicating again that like charges repel.
But there's another type of electroscope, more common, and I just want you to know both of the types, where the leaves hang down like this, and then if the bottom of the leaves get charged up, the leaves repel each other and move far away. By leaves, I'm talking about metal that is very thin and able to move. Usually they use gold foil or something very, very light, pounded out type of metal.
The foils or leaves will still repel each other. You probably already know that if you hold a charged object like this negatively charged piece of vinyl near the terminal of an electroscope, the foils or leaves will repel each other. They move apart like this.
So here's an electroscope before anything happens. So if we have an electroscope that's neutral, and then we bring a positive rod near it, well, what's going to happen? Well, in this case, this is positive, so the electrons are going to move. They're all going to come up towards the top, and they're going to be attracted towards this rod. So that makes the top of the electroscope negative, and it makes the bottom of the electroscope positive. Well, what's going to happen if we have positive and positive? We're going to get repelling, so the leaves separate. If we get close enough that the electrons can jump, then the electrons jump across, making the electroscope overall positive, so that when we remove the rod, the electroscope is positive and the leaves will stay separated. Let's look at the reverse situation. We start out with a neutral electroscope, so the leaves are together, there's no repelling. And then this time, instead of a positive rod, we bring a negative rod near the electroscope. So what's that going to do to the electrons? Well, that's going to push them down to the bottom. So if the electrons get pushed down to the bottom, then we're going to have the top of the electroscope, sometimes called the knob, ends up becoming positive and the bottom becomes overwhelmingly negative. If the bottom's overwhelmingly negative, the leaves will separate. If we get close enough, remember this is super, super negative. If we get close enough so that we either make contact or the electrons jump, then the electrons will move over to here. This stays negative, and the whole electroscope will be negative, so that if we remove the rod, the leaves will stay separated. There's a device used in physics called the Van de Graaff generator, and hopefully your physics teacher did this demonstration. But if not, here's how it works. A Van de Graaff generator is a device. It has a metal sphere that acts as a conductor on the top, and inside there's a rubber band that spins around, and that rubber band picks up electrons and distributes them on the metal sphere. So if a person is standing on an insulated surface and they touch the Van de Graaff generator, we're going to get conduction. So electrons are going to run through the person's arm into their whole body. and we're going to get something that looks like this. And if the whole body is overwhelmingly negative, the body is actually going to repel itself. But hair is so light that the electrons will be able to actually lift the hair so that the hair ends up standing up, and the shape of the hair is actually in the shape of the electric field. Now, some Van de Graaff generators work the other way. They take electrons off, making this positive, in which case electrons would repel, making the hair positive, and the hair would stand up. Either way, a charged person, negative or positive, will have their hair standing up due to repulsion of like charges.
This is great. This is how we teach kids about electrons and really an electron elevator and how it sends the electrons over the top here. So here's what happens. There's a crank that's here.
Right.
The crank's going to turn the motor on the bottom. And when I turn it like this, you're going to actually start to feel some of the, oh, do you feel that? There's a little electricity that's in the air. Is that weird? All right, so here's what I'm going to do. You hang on to the ball, okay? And I'm going to hold on to this little grounding thing over here. And Vinny's going to dim the lights a little bit, and I'm going to twist it. And watch what happens here. You're going to get a nice little, get a little closer. Oh, there you go.
When we turn the motor on, that belt starts to spin really fast, and as it spins, there's a little metal cone that strips away electrons.
There's something called a Faraday cage. And what a Faraday cage is a roughly circular object, it doesn't have to be perfectly circular, made out of a conductor. And so this conductor, if we hit it with electrons, we put tons of electrons on it, the electrons are free to move on the conductor. Well, what are they going to do? They're each going to repel each other. So we actually end up getting electric fields that are opposite each other. If you think about the direction of the electric field, it's opposite the negative. And what's going to happen to all these electric fields that go in opposite directions? Well, they're going to cancel each other out. And that produces an electric field of 0. That's why if you have a metal conductor, think about inside of a building that has lots of pipes and electrical wiring, those electric wires shield you, and it's why you have a more difficult time getting the electric signal to be able to have your cell phone get service. The same thing is true of a car getting struck by lightning. Lightning is a flow of electrons. The metal sphere mutually repels the electrons, making the electric field inside the car 0. It's not because of the rubber tires. In fact, the rubber tires make it worse because the rubber tires prevent the electrons from running off of the car. So it's very dangerous if your car gets struck by lightning and you step outside of the car. Now, if you touch the car, all those excess electrons on the outside will shock you. I'm sure that you've heard the term ground or an object getting grounded. Well, what does that mean in physics? Well, it's an object that's so large it can accept, meaning gain, donate, give many electrons without changing its own charge. So one of the best things that works like this is a lightning rod. A lightning rod is used to actually drain off charge from a cloud. So if a cloud gets built up a whole bunch of charge, let's say the cloud becomes negative at the bottom of the cloud, and electrons can start to leak off and go to this pointy metal object and run down through this metal into the ground. Why is it called the ground? Because the ground is the Earth, and the Earth is very large and can take many electrons without changing its own charge. If the cloud was positive, electrons would travel up, neutralizing the house and keeping a lightning strike from occurring. If a lightning strike does occur, it will hit the lightning rod, and rather than go into the house, it'll take the shortest path into the ground by following this conductor, this metal wire. We can also look at a charged electroscope. Let's say the electroscope is charged negative, so it has more electrons than protons. If the person who is touching the ground touches this electroscope, then electrons will run through the person into the ground, but not all of them. It will only take as many until the object goes back to neutral. So right here, oh, we need one more. Oh no, that's right. So now it goes back to neutral and we have the same amount of electrons as protons. So the person grounded the electroscope, bringing the electroscope back to neutral, and the leaves would come back together. How does lightning work? Well, with lightning, we get a separation of charge. So frequently we have electrons go to the bottom of the cloud, but we can also have the opposite occur. Sometimes the bottom of the cloud becomes positive. But let's treat this with the electrons at the bottom of the cloud. If the cloud gets close enough to the ground and the charge is big enough, we will get conduction. We will get electrons jumping down to this tree or some other object. So here's the electrons jumping down. Now, the lightning is two effects. Essentially, the air gets very, very hot because the electrons are traveling through an insulator, and electrons don't like traveling through an insulator, and that process produces heat. As the air heats up, the electrons that are attached to the atom get removed, and you get what's called a plasma. And the plasma is the electrons that are free to travel down this path. Well, when it cools, the air moves back together very quickly, and that is what produces the boom or the thunder. And also the electrons falling back onto their atoms, that produces light. So we get two phenomena. We get a flash and we get a boom. The lightning, what we see, and the thunder, what we hear, are one phenomenon that happen at the same time. But light travels much faster than sound. Therefore, the light will get to you before the sound does. And that's why you see the lightning first, then hear the thunder second. Now, I drew this as a wave because light is a transverse wave, and we'll learn about that in the waves unit. And sound is a longitudinal wave, which is the vibrations of the air moving back and forth in this direction. So, which do you see first? The flash, then you hear the boom, but by how much? Let's say that this person is standing a mile away from where this tree gets struck. A mile is roughly 1,600 meters. So let's do the calculation. You can figure out the speed of light. It's on the reference table, and it says speed of light in a vacuum. In air, it's roughly the same, which is 3 times 10 to the 8th meters per second. So we know the distance, 1,600 meters, and the time it takes for light to go a mile is 0.0000005 seconds. In other words, it's so short that we can treat this as essentially zero. It's not zero, but it's so small we can't detect it. Now for sound travels at only 331 meters per second. Speed of sound at STP is on the front page of the reference table, so they give you this number. And we know that this is 1,600 meters, so we solve for the time, and that's 4.8 seconds. So the rule of thumb is that if you're standing and see a lightning flash, you can count. And if it takes 5 seconds before you hear the thunder, you know you're a mile away. If it's 10 seconds, you're 2 miles away, and so on.
Lightning is the discharging of electricity, usually in the midst of mature thunderstorms. It can be inside a cloud, from one cloud to another, from cloud to air, or cloud to ground. Cloud to ground lightning occurs when there is an electric potential gradient inside the cloud that causes electrons to discharge towards the ground. Negative cloud-to-ground lightning occurs when the stroke carries negative charges from the cloud to the ground. This is the most common. 90% of all lightning is cloud-to-ground lightning. Most lightning strokes are negative strokes, meaning that they have a large concentration of negative charge in the cloud base and a concentration of positive charge on the ground. Positive cloud-to-ground lightning occurs when the base of the cloud is positively charged and the ground negatively charged. Positive strokes are most common in severe thunderstorms just prior to tornado formation.
Voltage is a particularly tricky concept. The first thing that you need to know about voltage is that it has a couple of different names, and those names are potential difference and potential drop. So you need to memorize that because they use these interchangeably. Voltage is a scalar. It doesn't have a direction to it, unlike the electric field, and the unit for it is the volt, which is just a capital V for the unit. And essentially what voltage is the work done per unit charge. Now, what does that mean, work done per unit charge? Well, I'll tell you here in a second. There's a formula for it, and that formula is equal to W over Q. And in the next video, we're going to use this to solve some problems, and we'll put actual numbers in it. But right now, I just want to go over the idea of voltage. So, let's say we have a large positive charge. We know that we have an electric field, and that electric field moves outward, but as it moves outward, it gets weaker. So let's pick a particular point here, like this. At this point, the electric field E is very strong. And if we go out here, then the electric field is very weak. So we have a weak electric field here and a strong electric field here. So what we say is that the electric potential from here to here changes. So we have a high electric potential and a low electric potential. And the difference between these electric potentials is called the electric potential difference, and that's what voltage is. Specifically, it is the work for a certain amount of charge that we move from here to here. So let's say we take a proton and we push that proton over to here. That's going to require work, and the work done per charge that we have is going to be the value of voltage. Now, there's a couple of other things that you should know about with voltage, which is this is why a bird can land on a high voltage wire and not get shocked. The bird is at 10,000 volts. But being at 10,000 volts isn't a problem unless you're next to 0 volts. So if the bird was able to, let's say they had a leg that was very long and they touched the 0 volts, then the 0 volts to 10,000 volts would be a potential difference of 10,000. That's dangerous. But if you're only at 10,000, then you're at an electric potential of 10,000 and there's no electric potential difference. So another way for me to explain this to you, Denver is called the Mile High City. When you're at the Mile High City, you're a mile above sea level, but it's not dangerous. You're not going to fall anywhere because you're at the same height. Everywhere you go is 1 mile above the sea level. But if you stood next to a large cliff, now you're very close to the ground, and if you fall, that height difference is dangerous. The last concept that we're going to talk about is current. Now, if we have a large negative charge and a large positive charge, we have a difference in electric potential. What does that mean? We have an electric potential difference. So we have a voltage. And when we have an electric potential difference or an electric potential drop, the electrons are going to want to move from the negative to the positive. So the electrons are going to flow along here, and as they move along, they are flowing like water in a river. Well, what do we call the flow of water in a river? Well, we have a name for that. It's called current. So in physics, current is the flow not of water, but it is the flow of electrons. So it's a rate formula because it's how quickly the electrons flow. The symbol for current is kind of strange. It's the letter I, capital I. And because it's a rate, it's how much charge flows in a certain amount of time.